upright. Is that the better?
No,
It's
better if it's horizontal.
Oh, okay. Okay. So just start over again? Okay. Did you get this part? Review question, chapter 6, 60 to 70.
Wait, is it all of them?
Even then.
Yeah, I try to give you 10 questions or so.
That's too much work.
How about just
Oh, dude, they're so easy. I would just calorimetry.
coffee cup calorimetry.
None.
Oh, but that's no.
Some of them are hashes.
Okay, that's good. Let's all talk at once.
You changed the numbers last time. That's not fair. I had to think on the quiz.
Oh my gosh.
It was terrible.
I did something unfair. I'm sorry about that.
I think all quiz questions should be like, what's on our labs, straight out of our labs, straight out the book, okay, and straight out of these lessons.
Yeah.
I think this is how we learn.
Yeah,
Repetition is the best
Thank
way
you
to
all.
learn.
Great suggestions. The last time that we had a lecture, which was last Wednesday, I had just started talking about electrolysis. Electrolysis is going to require an external power supply. This thing right here is the key for electrolysis. This thing has a negative terminal and a positive terminal. What I want you to remember is the negative terminal is always going to have the electrons coming out of it. So which side, the left side or the right side, is going to be the negative of the power source?
Yeah.
The left side.
Nope. The electrons are coming out of the power source from there because the electrons are going that way and coming out that way. So this side would be positive, this side is negative. Remember, and I'm going to show you a power supply here in a couple of minutes. This thing has a positive terminal and a negative terminal. The electrons always come out of the negative from the power source. So this is the electrons coming out of it, and they're going this way down into this terminal.
Wait, I don't quite get this. Why is the NaCl like a cathode and the anode?
Because we have melted down salt. It's not salt water, it's just salt that has been melted. It's liquid salt.
Oh, it's pretty hot.
It's about 800 degrees Celsius. In liquid salt, you have sodium ions and chloride ions. And what else? Right, nothing. Nothing else.
That's why
Very insightful. Good answer. So yeah, when you have liquid salt, there's just sodium ions and chloride ions. So if the electrons are going out from here and then into here, what substance in that liquid salt is going to give off electrons? There's not much choice here. It's either going to be the sodium ions or the chloride ions. Can the sodium ions give off an electron? No, they've already given off an electron. They have a positive 1 charge. It has a noble gas electron arrangement. There's no way that it's going to give off one of its electrons in its core electron. That does not happen. You've got to really work for it if you want to take the electron off of the sodium ion. So the chloride ion. Now the chloride ion is very stable as a chloride ion. It doesn't want to give off its electron, but this power supply is going to have its voltage turned up. It is going to require the chloride to give off the electrons out of here. So the 2 chlorides are going to give off 2 electrons and make chlorine gas. So as this thing oxidizes, as the electrons go out of there, the chloride ions start bubbling from that electrode. You're going to see bubbles coming off of this electrode. Bubbles of chlorine. Room-clearing chlorine.
Did anybody make chlorine on
dang it! I should have this.
I know a lot of people were
I
trying
knew I could have made 800.
Some people were trying to.
Yeah, because they wanted to see the yellow.
Kelly, I'm looking at you. But no, we didn't make any chlorine. You might have made some chlorine. Did you make chlorine?
I heard. I smelled it. They did.
Kelly doesn't want to talk to me. So she doesn't want to look
Not
at me.
my group. I died from it.
I saw smoke
There's
coming
the
out of
hydrogen. All right. So anyway, as the electrons come into the cathode, reduction has to occur here. And since the reduction is occurring here, something has to be gaining electrons. Now the chloride ion, then there's lots of chloride ions in here. The chloride is not able to gain electron. It already has gained electron, that's why it's chloride. So the only thing that can gain electron is the sodium ion. It's going to gain electron and make metallic sodium. It does not like to do that. Sodium is more stable as an ion. But since it doesn't have a choice as a result of this power source, then the electrons must come in here and they must be accepted by the sodium. So this is a way that you can take salt and turn the reaction around to make it go that way making sodium and making bubbles of chlorine gas. This is how in industry, if somebody needs pure sodium metal, they're going to do that. They'll melt down salt and electrolyze it, and they'll scrape the metallic sodium off of there, and then they'll use it for whatever they have to use it for.
It's like it's way too easy. Like you just stick something in there and it does it for you.
But melting the salt down is not so easy.
Oh,
They have
yeah,
to come
okay,
up
yeah,
with
too.
a way of melting it down. So it's not a simple process at all. I can't show it to you because I don't have anything that can withstand 800 degrees. Like my dishes would all break. I don't even know if the Fisher burners can get up to 800 degrees. So we're kind of stuck.
Try to school, maybe to school.
Doing it on paper. All right, Spencer, let's go to the next one. So when you have a liquid salt, any salt, like potassium fluoride or sodium chloride or any salt, it's pretty easy to identify what's going to be the anode and what's going to be the cathode because you don't have any other choices. You have one thing that will oxidize possibly and one thing that could possibly reduce. When you have solutions of things dissolved, that's not so obvious. And that's what we're going to be talking about today. You have a good picture of what's on the board here? You're going to need a reduction potential table. You still have it?
I might have misplaced it somewhere.
You can pull one up on your phone, just Google it.
Kidding.
Oh, yeah.
I can't hear you.
I gave you one, Jessica. Is this it right here? Or is that thing I just gave back to you?
Wait, what the heck? I kept my
The next one
Pretty good
is
backpack of yours.
the 17th, Monday. Whoa, what? Tuesday, the 5th.
Does he take chemistry? Yeah. You should ask him. He probably. What if he's like really smart in chemistry?
Maybe. I hope this correct me, then I'm going to
And,
fool.
oh, and Friday. I lied to you, Gary. Did you hear me, Gary? Next Monday and next Friday.
I don't. Why are you putting...
Michelle, does he know chemistry? You should ask him.
We good? Everybody has one?
Can't use it at all.
Spencer, let's move on to the next one.
No, the problem is the card that it's used against is...
All right, can I have your attention, please? We're going to be looking at, first of all, the electrolysis of just water, and then we're going to look at solutions of things dissolved in water. This is a spontaneous reaction, just like sodium plus chloride, or chlorine makes sodium chloride. Water is made from hydrogen, the element hydrogen. This is not hydrogen ions, the element hydrogen, and the element oxygen makes water. Is this a redox reaction? Yes, oxidation numbers are changing. So since it's a redox reaction, the cell potential can be determined by looking at the reduction potential table. Can you determine the cell potential for this thing? Identify who gets oxidized and who gets reduced. Find their potentials and add them together. You have to find two half reactions.
That might require some thinking.
It does.
Guys, come on. Like,
Find the reduction first. Who gets reduced?
Oxygen.
Yep. Oxygen goes from 0 on the left to -2 on the right. Does everybody see that the two terms on the left are zeros? H2 is 0 oxidation number and oxygen is 2.
So it's 1.23?
Yes. Everybody find this? 1.23.
Yeah.
You see it?
Yeah.
Okay, so the hydrogen is being reduced. This one is not as obvious. What is the... I said the hydrogen being reduced. That's wrong. The hydrogen is being oxidized. What's the oxidation potential of hydrogen?
0.
No. You're looking at hydrogen making hydrogen ions. This is not hydrogen ion, it's H2O. So you need to find, we're doing an oxidation here. You need to find water reducing the hydrogen gas and then turn it around?
Oh, 0.83.
Yes. Yeah, it's going to be 0.83. Spencer, slide down just a couple of lines. There they are right there. Now, the one that you were trying to use that had 0 has hydrogen oxidizing. Nope. This oxidation is not appropriate because we don't have hydrogen changing to hydrogen ions. This is like for an acid, where you have hydrogen ions that are free. This is hydrogen tied up in water. So remember, water is a molecular compound. It needs to stay together. So you can't use that one for water. These two half reactions are used. Now I want you to take a look at this, and I want to ask you, do these two half reactions, this is our oxidation half, where the hydrogen is 0 there, going up to positive 1 there. This is our reduction half, where the oxygen is 0, going down to negative 2. When you add these two half reactions together, do you get that reaction?
No.
You have to do something first. You have to multiply what? The top reaction by what?
2.
Right. Now if you multiply this one by 2, and then you add them together, does that give you that reaction?
No.
No.
Let's take a look.
Actually, yeah.
All right, copying this thing down. 2 OHs plus H2 yields 2 waters plus 2 electrons. And you have 4 electrons in the next reaction, plus 4, hydrogen ions, plus an oxygen, makes 2 water. Okay, now we know that we have to multiply this thing through by 2 to get the number of electrons equal to each other. Don't add 2 half reactions together unless the electrons are equal. So that's going to make 4 hydroxides plus 2 hydrogens yields 4 waters plus 2 electrons. Now, sorry, thank you. I'm going to erase this top one now that I've fixed it and add these two together. When you add these two together, you see you have hydrogen ions here and hydroxide ions in the next one that you add together. What do you do when you have hydrogens and hydroxides on the same side?
Make a water.
Make waters out of it. So we can take this and make 4 waters. And yeah, how many waters do you have on the right? You have 6 right now. You got 2 there and 4 there. So those 4 can cancel those 4, and now we're looking pretty good. The electrons cancel out of 2, and what are you left with? 2 H2s plus an O2 yields 2 waters. That does add up to those 2. Yes? So what is the cell potential? That plus that. 2.06. Now, is everybody comfortable? I know this is kind of weird because we're not used to it. We had to double this oxidation half reaction. What did you do with that?
Leave it.
Didn't do anything. Why? Why is that? If you double your concentrations and everything. But remember, I should have had a degree sign up for both of those. Shouldn't I have?
Yeah.
Those are the table values. Table values imply that your concentrations are all at 1 molarity. Your gases are all at 1 atmosphere. Whatever the coefficients of this thing are, if I have to double the coefficients, that table value doesn't change. It still is implying that your solutions are at 1 molarity. So don't mess with your numbers off the table. Okay, even if you have to multiply a half reaction through by 2, don't change the cell potential. Spencer, let's move down. Stop. So, combine that plus that yields 2 waters. The cell potential is going to be 2.06 volts, positive. So that means that this reaction in that direction is spontaneous. It's got a positive cell potential. By the way, this is the reaction that we're hoping for the future. This is the fuel cell reaction. It's just hydrogen combining with oxygen to make water.
We're making a fuel cell?
No, we're hoping for that in the world for the future.
Oh, good.
Fuel cells are right now being made. The problem with fuel cells currently is that it takes more energy to get these two reactants than the amount of energy you get out from making water from it. So they have to figure out how to produce hydrogen without using too much energy.
We did it in class.
Can they do what?
Yeah,
That's